All right, kids, so in today's lesson, we're going to kind of get started with limits and continuity, but we're just kind of more doing an introductory thing today into calculus. And as we look at the very first part of this, we're going to study today about can change occur at an instant? And this is kind of a major focus point of the entire course is a rate of change at an instant. Now, first, when you look at the fathers of calculus, you got two gentlemen who are kind of credited with being the fathers of calculus. You have over here on the left-hand side, Isaac Newton. That was in London, England, or just England. Let's just go with that one. And then the other one would be Gottfried Leibniz. And I guess it all depends on how you want to pronounce his last name, but here's the spelling. But again, both of those men, Newton was born around 1643. Leibniz was born around 1646. And both were developing calculus at about the same time. Some historians think that one stole stuff from the other one, and vice versa. But it just happened that they were both brilliant men that were kind of thinking about this at the same time. And they exchanged papers back and forth and kind of helped form calculus. And a lot of the things that we deal with, and other mathematicians built off of their work over the centuries. So first thing we look at here, this first example is, can change occur at an instant? Mr. Brust's distance from his house is modeled by the function d of t. While riding his bike to the store, again, store is basically over here, if you want to think about it, he realized he dropped his wallet, turns around and to find it. So as you look at this, as you look at our little picture here, he leaves his house down here at 0, 0. He leaves his house, starts riding away from his house, gets to some point and realizes, oh, I forgot my wallet, so I'm going to start going back to where I can find it. He eventually found it, and then we turns and starts going back to the store, and then finishes up there. And so now what we look at in these questions is, what is the average rate of change for the trip to the store? And when we think about average rate of change, and first thing we teach you way back in middle school is we can find the rate of change of a linear function, but what happens when it's a nonlinear function? We can't really find the slope of a nonlinear function, and that's true. But we can find the average rate of change between 2 points on that function, that nonlinear function. So we're going to keep the same thing in mind here when we think about average rate of change. We're going to be thinking about the slope formula. We're going to think about the change in y over the change in x. And so with this in mind, what is the equation, if we had an equation, d of 8 minus d of 0 over 8 minus 0. Okay, so again, we got two ordered pairs. We got 0, 0, and we got 8 and 1300. So as we keep filling this out, we got 1300 minus 0 on top over 8 minus 0. Simplify that a little bit. And we get roughly 162.5 meters per minute. Now, we're going to be doing with a lot of rate of changes of different things. So we're going to make sure we keep the units on there. Every time we're talking about a rate of a change in some form or fashion, we want the units on there. And so we don't ask me, do we need to put it on there? Got to put it on there. So that's kind of the setup here, that on average he was traveling 162.5 meters per minute towards the store. Okay, towards the store. All right, so now let's take a look at the next part. What was the average rate of change from minutes between the 2 and 6 minutes? So with that in mind, keeping the same format, that would just be d of 6 minus d of 2 over 6 minus 2. Now, we really can't find that. We're just kind of set up the equation there is what we're looking at it, is to see, okay, what will we roughly do? And again, we don't have the ordered pairs, and we don't have an equation that goes with it, so we really can't get too fine in the details of it. But I want to point out one thing here. If we take at 2 minutes and highlight that ordered pair right here, and then at 6 minutes and draw a line between those two pink dots, We just created the secant line is what we did. We created the secant line. And so we can find the slope of that secant line. Like if we wanted to do rise over run, we could roughly find what that slope of that secant line is. My point here is that slope positive or negative? We can tell what the line is doing from left to right. And then with that in mind, that means our answer for our average rate of change should be what type of a value here. And then what does that mean in the context of the problem? I think as you guys are probably answering those questions in your mind, obviously that's a negative slope line. So the slope is the average rate of change is going to be negative. And then what does it mean for it to be negative? Well, in my mind, it means that, hey, he's going away from the store. He's not traveling towards the store. He's traveling away from the store. Again, the very first answer was a positive because he's heading towards the store. So in my mind, I think it's negative because he's heading away from the store to try to find that wallet. He went backwards, maybe towards the house. He's tracing his steps. Part C. Part C wants us, what is the average rate of change between minute 2 and minute 3? Same thing here. We're going to set up just in general D of 3 minus D of 2 over 3 minus 2. And again, as we decrease our intervals here, we're going from 0, D of 8 to D of 0, and then we're going to D of 6 to D of 2, and now D of 3 to D of 2. We're getting our interval between two order pairs to be smaller and smaller and smaller, which is leading us to the next topic here is it possible to find how fast he is going at an instant? And that instant is called the instantaneous rate of change. Got to pause there so I can make sure I spell everything right there. So we got the instantaneous rate of change. Instantaneous rate of change is a huge fundamental piece of what we're doing throughout the course of calculus. We're talking in a lot of different aspects. How is it changing at that one particular instance? And we'll analyze if it's positive or negative, and in certain contexts it means other things. So very key thing that we're doing here. As we look at it, give an example of how to calculate a rate of change that would give a close estimate to the instantaneous rate of change at 2. Well, I'm going to zoom in here on our little graph here, change my little colors here to something. I'm going to use the green one. And if I was going to say, okay, let's try to figure out, well, how can I find an instantaneous rate of change trying to use some order pairs? Well, if we happen to use like order pairs of 1.9999 and 2 for the x values, and then we would actually, figure out what the corresponding y values are. And that's going to put us two places. That's going to put us two places on this graph, but they're going to be super close together. They're going to be really close together. And so with that in mind, we end up getting, as we draw the line between those two ordered pairs, it no longer becomes a secant line. That line, because they are so close together, they almost look like the exact same point, end up being called what's called the tangent line. Now, we get to talk more about the tangent line, the equation of the tangent line in Chapter 2, but that gets us closer to finding what the instantaneous rate of change is. So, if we want to use a rough estimate here, let's say we start, and I'm going to put right at we're about halfway in between 900 and 1200 there. If I go up one full square, and that puts me right about there, and over one to the right, it kind of puts me on that line there. So with that in mind, keeping the same theme, I basically went up 300, and then I went over to, and I believe our thing's in minutes, so 2 minutes. And so, boom, 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 come down here with the instantaneous rate of 2, we would say, well, that's going to be basically 300 meters over 2 minutes, which comes out to be about approximately 150 meters per minute. All right. Now, next question. Again, my Apple Pen, if you saw that little highlight's getting ready to die here. I got less than 5% battery. Real quick, these ones were just explaining what those things represent. Almost end of the lesson, then you can get started on the the worksheet stuff for homework, and I'll have those answers posted for you. Here it says B of T represents the buffalo population in the United States, where T is measured in years since 1800. What does B of 90 represent? Well, that's the number of buffalo in the U.S. or in the United States in 1890 is what that represents. Again, just basic Algebra 1 explaining what that number B of 90 represents in the context of the problem. Now, part B, a little bit different. They're given that little slope formula. So we need to think about, when I see that little slope formula, I want to think about the average rate of change. So we got the average rate of change of the buffalo population per year from 1800 to 1850 is what that represents. Now, last one, getting a little bit more precise here. We notice how they're getting it to be a closer and closer X values for what we're doing there for testing our little average rate of change formula. Well, this ends up being an estimate of the rate of change of the buffalo, of course, in the United States buffalo population in the United States, so U.S. per year in 1832. All right, that gets us closer to, okay, how did it actually change in that year roughly, is an estimate of what that changed in that buffalo population. Again, that's it for the notes. Next several pages here, as I'm just going to scroll up here, that's the rest for you to fill out here in class, kind of doing the same thing, going through problem by problem. You can work together. I will post an answer key a little bit later for you to be able to look at, and I'll probably stick it in, I guess, the answer key folder. I'll create an answer key folder, put it out there for you guys, and that's where I'll put the answer keys for the homework each time when we do stuff. All right, got any questions? Shoot me a message. Hope you have a great day.